In this lecture, we will discuss measurement system analysis. By the time you're done with this lecture, you should understand what the different aspects are that make up your measurement system, how to evaluate your measurement system, what levels are acceptable, and how to identify areas of improvement. What is a measurement? Well, C. Eisenhart defines a measurement as an assignment of numbers to material things to represent the relations among them with respect to particular properties. Okay, that's great, but why do we care? Why do we measure? Well, we measure because we need a way to evaluate our process or product. We need to track improvement and compare methods. If our measurement system isn't good, we won't be able to do any of the things with any confidence. Many times, people just assume that all measurements are exactly correct. In this module, we will talk about what makes a good measurement system. We measure all kinds of things. Some seem more scientific, like the pH of a solution or the wavelength of light. But just because it sounds like a scientific measurement doesn't necessarily make it an easy thing to measure. The difficulty with measuring a student's performance or the public's opinion are a bit more obvious, although I'm not sure all professors understand the frailties of the measurement systems they use. The total observed variability has two parts: the actual variability in the product and the variability in your measurement system. It would be ideal if the tool measured the important characteristics exactly, but we know that this is not the case. The amount of variability within the measurement system adds to the overall variability. The relationship is given on the slide. You can see from this that the less variability that we get from our measurement system, the better. Let's motivate the idea of a measurement system analysis with an example. It was decided that body temperature was a key process input variable for a Six Sigma project in a hospital. Body temperature was measured with an ear thermometer. The specifications for this variable were between 35 degrees Celsius and 40 degrees Celsius. The project leader wanted to run a measurement system study on the process of making the measurement. She created the study having each of 3 nurses check the temperature of 10 patients twice in both the left and right ears. The results are given on the next slide. Here are the results of the ear thermometer measurement system study. Notice that we have 3 nurses, 10 patients, 3 measurements, and both the left and right ears were used. For the study, let's assume that we only use the data from the left ear. Also, notice that the measurements were made to tenths of degree. This will come into play later. Notice also that we could easily use some of the basic graphical and numerical summary techniques to see what is going on here. Let's hold off on doing that for the time being. Here are the criteria for assessing your measurement system. We will discuss each one of these concepts. We will first discuss stability. Stability is the idea of consistency in your measurement process. Your measurement process should exhibit a constant mean and variability across time. We should not see any sort of patterns, such as trends or oscillations. We can assess this idea by creating a series plot, or what we might consider a run chart, of the data. Here is a series plot of the ear study. We can see from this we may have a couple of points that are lower in temperature than the rest, but I don't see this as an issue. I would conclude from this that the data is fairly stable. Now let's discuss measurement tool discrimination. Discrimination is the smallest increment that can be distinguished by the measurement device. But just because the scale shows small increments, it doesn't mean that the instrument can actually read correctly to that resolution. There are some examples of tools and their discrimination given in the slides. You should be able to see that it really depends on what you are measuring with the tool. You wouldn't want to measure something that weighs 5.12 grams on a bathroom scale that measures to the nearest pound. So how do we decide if your measurement tool has adequate discrimination? We will do this by looking at the number of distinct values within the data set. If we have less than 5 different values within the data set, then we can conclude that the measurement units are not adequate. If there are exactly 5, we can conclude that the measurement units are borderline. If there are more than 5 different values, then we can conclude that the measurement units are adequate. We can assess this by viewing a plot of the data or just by looking at the data itself. Now let's go back to the ear thermometer data. Here is the series plot of the data. Notice here that based on the plot, we indeed have more than 5 distinct values for the data. We can conclude here that we have adequate discrimination for our tool. Now let's take a look at the data and round it to the nearest 1 degree C. Here is the plot of the rounded temperatures. Notice here that we only have 3 distinct values for temperatures, 36, 37, and 38. We would consider this measurement tool to not have adequate discrimination since there are less than 5 distinct values among the data. If we repeatedly measure an item for which we know the true value, say a standard gauge block, then the bias is the difference between the average of the measurements and the true value. Precision is the variability of the measurement system. In other words, if we measure the same item repeatedly, precision is the variability among the measurements. You often hear the word accuracy. Technically, accuracy means the same thing as bias, but people tend not to be very precise about their use of the word accuracy. Let's make sure what someone really wants or needs when they say accuracy. Any measurement we take is a combination of the truth, the bias, and the precision. The thing that we hope for is precise, unbiased measurements. An easier problem to fix is bias. Usually, it is easier to shift a process than to reduce variability. There are 2 components of precision. Repeatability is the variability of the measurements on the same item under identical conditions. If one operator repeatedly measures the diameter of a shaft with the same caliper. Another might be a blood analysis repeated in the same lab with the same technician with the same instrument. Reproducibility is the variability of several different operators measuring the same item. This slide shows the results of the same item being measured by 3 operators. The variability within the individual distributions is each operator's repeatability. The variability between the operators represents reproducibility. A gauge R&R is a study used to assess the level of precision in your measurement instrument. It determines the percentage of variability due to the repeatability and the components of reproducibility, and then compares measurement variability to the specification for the variable of interest. Now you are ready to run a gauge R&R. We need to decide on certain things, like how many operators, parts, and repeat measurements on each part by each operator. First, let's discuss parts. Unless you have standards for measuring that certain characteristic, you should use actual production parts. The parts should reflect the entire range of objects that your tool could measure. For example, if your tool is a scale that you use to measure a range of weights from 1 kilogram to 100 kilograms, then you should not use all parts under 5 kilograms. Usually people like to use at least 10 parts. Now let's move on to operators. You should make sure that you use operators that will use the tool regularly. In terms of the number, more is better than less. This will give us a better estimate of the operator variability. The number of trials or repeat measurements on the parts is important since it allows us to assess the variability due to repeatability. As long as we have enough parts and operators, the number of repeats can be 2 or 3. For the study, you want to make sure that things mimic normal methods as much as possible. So there should be no additional training given to the operators. Also, there should not be any additional calibration or such on the tool. You want to make sure that you use sound statistical techniques. You should make sure that the trials are randomized as much as possible with respect to part and operator. Also, it is not a bad idea to make this study blind to the operators. So in other words, the operators don't know which part they are measuring or what value they got the last time they measured a part. Now let's go back to the thermometer study. By looking again at it, you should be able to see that it is a gauge R&R. We will use the results of the study to assess the precision in the thermometer. Now that we have learned about gauge R&Rs, let's use the thermometer study and identify the sections of the study. So based on the information that we have, you should be able to see that the patients are the parts, the nurses are the operators, and the repeats are the multiple temperature measurements made on the patients by the same operators. So now we need to consider how to analyze this. We will be using the numerical and graphical techniques that we know and love, only put together in a specific way. For graphical summaries, we will use the plots of the mean temperature reading based on parts, operators, and parts by operator. We will be looking for any sort of patterns or extreme values. Here is the plot of temperature means based on part by operator, or in this case, patient by nurse. Based on the plot, we have the average reading on the vertical axis and the patient number on the horizontal axis. Then each line represents the readings made by a different nurse. Based on the plot, we can see that the overall pattern across patients is pretty consistent based on nurse. We do see that nurse 1 has consistently found lower readings than the other two except for patients 8 and 10. Also, nurse 2 and 3 are very similar in their readings except for patient 9. These are situations that you might want to investigate. Here are the plots of the individual values of temperature by nurse. The red dots represent the individual values and the black dots represent the means. You can see that the mean for nurse 2 is somewhat higher than the other two. This could be because both nurse 1 and 3 measured a value lower than 36.5 degrees. This last graph is one where we see temperature measurements based on patient. It not only shows the average by patient, but also the individual values so that you can assess variability within a patient, which is where repeatability comes from. You can see that there is a lot of variability within patient. This is especially apparent for patients 2, 6, 7, 8, and 9. Also, we can see that both of the low values on the previous graph come from patient 9. This, coupled with the other issues with patient 9, warrants some investigation. So based on the graphs we just looked at, we can conclude that there is large variability between parts. There is large variability within parts, which of course is repeatability. There is small variability between operators, which is what we consider reproducibility. Now, let's see if the same ideas come out with numerical analysis. For numerical summaries, we will look at the percentages each component makes up based on the overall variability. We will also see how much of the width of the specification does the measurement variation take up. Let's start with the percent contribution to the overall variability. The percent contribution is used to assess the percent of the overall variance that is explained by the measurement system. The overall variance is made up of the variation due to different parts, repeatability, and reproducibility. We can also use this to assess the contribution of individual components such as repeatability. We find the percent contribution by taking the ratio of the variabilities as seen on the slide. The precision to tolerance, or P to T ratio, is the ratio of the measurement variation to the specification width. It identifies how much of the specification width is taken up by the measurement variation. The formula for finding this ratio is given in the slide. Now that we have these values, how do we know if the measurement system is adequate? So in a perfect world, these things would all be 0. Of course, we know that this is not possible, so we would like to make these ratios as small as possible. The Automotive Industry Action Group has set up standards for gauge R&Rs. It states that any one of these ratios at 10% or less is acceptable. Anything higher than 30% is not acceptable. Anything in between is suspect at best. Other companies have set up their own guidelines as well. Now let's go back and take a look at the thermometer example. Here are the results for the variance contribution. In this table, we have a column for source, the estimated variance, and the percent contribution to the overall variance. Based on the table, 26.63% of the variance is coming from the measurement system. This means that 73.37% is coming from parts. Broken down further, 22.31% is coming from repeatability and only 4.33% from reproducibility. So we can see that there is somewhat of an issue with repeatability. This is the table based on the P to T ratio. Recall that the spec limits for this study were 35 degrees C to 40 degrees C. So we find these numbers by dividing the values within the first column by 5. Based on this, the measurement system variation is taking up 23.19% of the tolerance. This variation due to repeatability is taking up 21.22% of the tolerance. We also see here a bar chart that represents these numbers. Based on the chart, we can see that the big issue in this case is repeatability. Now let's draw conclusions. Based on the numbers within the plot, the overall percentages are less than 30%, but not less than 10%. At this point, we may want to investigate what is going on when making multiple measurements, since the big hitter seems to be repeatability. A component of variability study measures the different sources of variability in any process. The previous gauge R&R study was a specific form of this type of study. In this example you see on the slide, fluid samples from the same batch are sent to different laboratories to be evaluated by different operators. Thus, we can evaluate three sources of variability: within an operator repeatability, operator to operator, part of the reproducibility, and lab to lab, which is another part of the reproducibility. These are hypothetical results like you might see from this sort of study. Notice the use of the pie chart here instead of the bar chart like we saw in the thermometer study. Here is a process map for the measurement system. This gives a good guideline on what to do and how to try to improve the process.